Today I'm going to be doing a webinar on how to use the Earthmover platform for predicting wildfire risk. It's going to include some slides and then some demo, and we'll go from there. So I'm going to just slide this here, and it's probably going to change my screen, unfortunately. Okay, so yeah, let's get going. So yeah, today we're going to be talking about wildfire. This is a satellite image from the Camp Fire in 2018. It's a beautiful image. It's also a devastating natural disaster that impacted a lot of people. And so what we're talking about today is like, how do we use data infrastructure and data science tools to understand these phenomenon, and then of course adjust behavior and all of that accordingly. So in terms of the demo we have today, I'm going to give an overview of what Earthmover is, what the platform, what our company is like, and talk for a few minutes about kind of the case study or the demo design, and then I'll jump into doing some actual hands-on work with the platform, and then we'll wrap up and have time for Q&A and that sort of thing. So, all right, so Earthmover, we are a public benefit corporation, started about 3 years ago. Our mission is to empower people to use scientific data to solve humanity's greatest challenges. And that includes climate, that includes biology, it includes energy, a bunch of different verticals, but really it's thinking about how does scientific data influence the lives of humans, and trying to build tools to help with that. So I started the company with Ryan Abernathy, my co-founder and our CEO. Both of us are scientists by training. He was a professor at Columbia for 10 years. I was at the National Center for Atmospheric Research. We were practicing scientists in our own ways, and bumped into the problem of, trying to do big data with scientific, big data science, excuse me, and really struggling to do that with the tools we had available to us. So that led us to start developing software. We met working on the xarray project. We're early contributors to both xarray and Zarr, started the Pangeo project. Gradually this became our main thing. And so now we have a company that's building tools specifically for these sort of applications. So we've been, like I said, working on xarray and Zarr for a long time. So what are those projects? Xarray is a toolkit and a data model for working with multidimensional arrays in Python. It has a really rich API. We're going to use it in the demo today, but think of it as kind of this Swiss Army knife of netCDF for in-dimensional array data. It's used super widely in this field. I assume many of you that are on the call have seen it or use it regularly. Zarr is a data format for storing large in-dimensional arrays in the cloud. So we call it a chunked and compressed format. It works by breaking up large tensors or arrays into pieces. We call those chunks, and then storing them in cloud object storage. And so the demo today will be using Zarr as the storage backend for an API for how to access data really efficiently in cloud storage. And then finally, more recently, we've developed IceChunk. It's a transactional backend for Zarr. So this is a layer on top of Zarr that is really meant for teams that are using Zarr in production. So how do you safely update your data using ACID transactions? So these are like database-like concepts. How do you do data version control? And how do you get the best performance out of it? And so IceChunk is really our solution in that space. So a couple slides on, what are the problems and solutions we're aiming to solve. The first is around, data organization and data governance. And, a lot of teams we talk to, they come to us and they say, yeah, we're using the cloud, but, we have this S3 bucket. It's just full of a bunch of netCDF and GRIB and HDF5 files. It's a total mess. We've got kind of the data swamp problem. And so, our solution there is to provide a hosted, centralized data catalog for those teams so that exactly what data you have, who has access to it, who's using it, and then updates to it are safe and mediated by these ACID transactions. So that's the core platform, is what we call Array Lake. I'll talk more about that in a bit. The next is really trying to squeeze the maximum performance out of your data. And this is particularly important for teams that are working with AI and ML applications, where you might be training a model, and the rate at which you can pull data out of your storage medium and into your model is directly correlated with how fast you can iterate on new ideas, and also your cloud spend. If you're training a very large model, training it twice as fast will cut that training cost down. So this is where IceChunk and Zarr really come in and shine. The ability to very efficiently pull data from cloud storage, maximize your throughput at the physical capacity of the hardware that you have, is a key part of what IceChunk and Zarr provide. And oops, went 2 slides there. And then finally, it's like, what do you do with the data once you've produced it? And one thing we see is, like, just like the data swamp problem, the end stage of the data lifecycle is also oftentimes just a spaghetti of different scripts and data formats, and trying to connect the dots between dataset A and user B. And so what we see is that many teams are trying to deliver basically the same type of data, but they're having to reinvent that entire stack themselves. And so with Earthmover, we have a set of APIs that really streamline this. So you put your data in IceChunk in the catalog, and then you expose that data via standard APIs. In our case, we're using the Open Geospatial Consortium's set of APIs that are just widely used in the field. So we'll use a few of those in a few minutes. This is what the architecture diagram looks like. So we have a layer that is the cloud service providers. So you bring your own cloud in most cases. You might have your own AWS account or your own Google Cloud account. You connect that with the Array Lake system. So we have a system for allowing you to bring your own cloud storage bucket into your data catalog. And then we provide everything that's inside the white dashed box. And so that includes the open source IceChunk library, includes the data catalog, and then all the data governance tools that I was mentioning. On top of that is the API layer for distributing data. So that's what we call Flux. We have a set of APIs there for distributing data via OGC EDR. So EDR stands for environmental data retrieval. This is a set of JSON style APIs. You ask for a time series at a point, and EDR will give you a JSON response or a CSV response, something like that. We also have OpenDAP, and then we have a tiles server for distributing data like in Slippy map tiles. It's useful to think a little bit about kind of like where all this fits in the typical life cycle of, say, an AI ML workload for scientific data. And we really aim to solve the data organization and management problems throughout the entire life cycle. So from ingestion, bringing in your existing archival formats of TIFFs or netCDFs or what have you, and then building that data cube of features for training or analysis, then actually doing the training, and then finally doing the inference and the data delivery, where you're trying to get your data into the hands of Python users or desktop GIS users, or into a front-end application. So that's the quick overview on Earthmover. And what I'm going to do now is spend a couple minutes introducing the concept of fire risk, and then we'll jump into the demo. So the core problem we're interested in is that in many forest and wildland environments, climate change is accelerating fire risk substantially right now. And so, understanding that climate is a key driver there, especially increases in temperature and changes in weather patterns, how do we adjust practices accordingly? And so, you know, in the use case for insurance, there's a actuarial challenge where, you know, we can't really use those historical fire observations as a good measure anymore because we have this non-stationary climate change driver. So what we see people doing is using increasingly data-driven solutions to try to estimate future fire risk to, to communities. And what I'm going to do today is use a set of downscaled climate predictions to estimate future climate risk. And this is a pretty tried and true process at this point. In fact, the slide on the right is showing future burned area estimated on a paper that I happened to be involved in some years ago. But like there are many papers about how to do this. The goal of today is not to teach anybody how to do fire modeling, but instead to show how the tools we have really accelerate your ability to do this. So if you're interested in like the science parts, feel free to shoot me a note afterwards. I'll shoot you some of my favorite papers. But today we're mostly going to be talking about kind of what is the data infrastructure needed and the data tools you need to do this efficiently. So, and uh-oh, my camera seems to have frozen. Hang on, folks, we'll be right back.
We can still hear your voice if you want to keep going, actually.
Okay, that's good to know. The Zoom thing has totally frozen. So I don't know what's going on there. Okay, I'll keep talking and hopefully my slide will advance when I'm ready to move on to the next the next slide. So, you know, the operational hurdles we see here are really that like the data sets that we're going to be working with today are massive. They're, you know, tens of terabytes in size. And so to efficiently do you know, analytics on this type of data, it just takes a well-designed data system. And so the goal of today will be to show kind of like what that might look like using our platform. So, okay. Okay, so yeah, the exercise that I'm going to walk through, I'm going to both show some give a tour of the platform, but then we'll run through a Jupyter notebook. We're going to take some data from the MACA downscaled climate projections. That is a set of 18 spatially downscaled and bias corrected climate models for the historical and RCP and 4.5 and 8.5 emission scenarios. And they have things like temperature, precipitation, humidity, et cetera. So we'll use those variables, and we've built a pretty simple empirical model to estimate fire risk based on inputs from a set of those variables. And the goal is really just to demonstrate how you can put all these together. And in a few minutes, we're going to have a map of future climate risk changes to fire. Oh, don't go to that one. Go to this one. Okay. So start by flipping over to a view of the Earthmover platform. And so here I've already logged into the Earthmover platform, and I'm looking at the data catalog for the Earthmover demos organization. And so here we have the you know, a set of repositories. You can think of the data catalog model as similar to GitHub. So you have an organization and a set of repositories. Those are each individually kind of versioned and managed data repositories. And then of course you have users and access control and all of that. So I'm going to grab the MACA v2 metadata, and I've actually been developing this data set on a separate branch. So I'm going to switch to that branch here. And you can see that, you know, 14 hours ago, I made an edit to this, this data set. And inside this data set are three groups. We have the historical RCP 4.5 and RCP 8.5 scenarios. And you know, I can take a look at any of those groups, and we can see that, you know, there are a series of variables and a set of metadata about them. So let's just take a look. You can see, you know, task min, so this is the air temperature, the minimum daily air temperature. And go ahead and grab that one. And we can see some metadata about this particular variable. So it's time by latitude, by longitude, by model. So I've included the ensemble dimension in this array. And so this is a 4-dimensional array. And we can see that, this is units Kelvin in this case. So we can do that for all of these. And if we want to actually use this data, we're going to need to jump into Python. And so that's what I'm going to do next. We provide some snippets for how to do this, but I have, of course, prepared a notebook already to walk us through how this will go. So with that, I'm going to jump into the notebook, and we'll come back to the web app at the end because we're actually going to create a data product, and we'll do some visualization in the platform there as well. So, okay, let's go ahead and restart kernel, clear all outputs, and here we go. So the basic idea of this notebook is that we're going to load up 2 of the scenarios, the historical and the RCP 8.5 scenarios. We're going to load them into xarray. We're going to apply our simple empirical fire risk model. We're going to create a summary layer that we might want to put in a web application or in a desktop GIS application for others to use, and then we'll also do some data visualization here in the notebook. So first thing I'm going to do is just do some imports. This is mostly open source libraries like xarray and NumPy and Pandas. So if you're familiar with the Python ecosystem, then you'll know many of these. I'm going to connect to ArrayLake using the ArrayLake client. So this is how we get access to that catalog. I've already logged in, so don't need to do that again here. And what I've done is I've checked out that same repository that I was mentioning previously, and the same branch, so the Maca v2 metadata branch. And so now I have this repository object. This is an ice chunk repository, and I've checked out a read-only session for the branch as well. And so we can see the latest commit, which was the same snapshot ID that we saw in the web app. The next step is to just set a few constraints for this. So we're only going to look at the Western US, and we're only going to look at the CAN ESM model for the sake of time here today. We're just going to do one model, but and from there we're going to load these data sets. And so xarray has this concept of lazy loading, and so I can load up this entire data set. Each one of these arrays is quite large. We can take a look. We can see that each array here for just this one model is actually, no, this is for all the models, but each array here is about a terabyte in size. And so if I were to load this all in memory, I would need a very large machine, but of course this is lazy loading, so we don't have to do that. So now we'll sub-select down to just a time window and a specific model, and we can see that this data is quite a bit smaller now. So that's loading the historical data, and now we have that data set ready to start computing on. We'll do the same thing for the future scenario, so RCP 8.5. And from here, we're going to apply our model. And so I'm going to see if I can grab this. We will add a cell here to just show what this model looks like very briefly. Won't spend a lot of time here. But this is an empirical model where we kind of weight the extreme, temperature, wind, et cetera, as separate parameters. And so we have this function that I've written, and we can now use this function to with our xarray data sets. And so the key thing is it takes this xarray data set as an input. Okay, so we'll go ahead and run that. And again, this itself is also lazy. So we're using the Dask backend to xarray here, which will allow us to do parallel computation here in a second. And what it shows here is that, we're going to get out about a 20 gigabyte array if we were to compute this whole thing. And so that's for the historical, and we'll do the same now for the RCP 8.5. And so what we've done here is calculate the daily fire risk for every every latitude, longitude point in the Western US for 1950 through 2100. So a bit more here, we're gonna like now calculate just mask out only the basically only the extreme fire days, and then we're going to create a statistic that is just the total number of those days per year. And so what we're really interested in is how often are the conditions ripe for fire. And this is one way to look at fire. There's other ways to look at fire risk, but today we're just going to be interested in, what's the one, how often is it super high fire risk. So we now have this extreme days for both historical and future. And here is where we're going to actually start getting ready to do some computation. And so, like I said, this up till now, everything we've done is lazy. We basically have a query plan that xarray and Dask have created together. And the next step is really to take that and to execute that. And so it's going to take a couple seconds to pull up my cluster, but while it does, I'm going to show just briefly, I'll talk through briefly what is going to happen next. So we're going to, the code on the screen here is not super important. The key thing is we're now going to actually trigger those computations and start to run them in the cloud. And so in this case, we're using a coiled cluster, which I had up here. That's going to generate, I think I put 50 different workers. So there's going to be 50 small machines running in the cloud. They're each going to be able to process work in parallel. And then, but the data is going to be streaming right out of our ice chunk stores and into those workers. And so in just a second, we should have all those up and running. And then while that's happening, I'll talk through how we're going to visualize this. And so, okay, so they're now, things are computing while I'm talking, and it'll just take a second. What we want to do is take a look at the spatial patterns of these changes in extreme fire weather. And so here I'm going to use xarray to calculate the time mean for these two periods. So we have a future period and a historical period, and then we'll have a change map. And so this change map is where we're going to get to see where the major changes in fire risk really have been. And so that is this. And so the rest of this is just matplotlib. So this is just Python, standard Python plotting stuff. And so while I was talking, the computation finished. So we processed terabytes of data in the last 30 seconds. And we can now make a plot of where fire weather has increased over the Western US. And so on the left is the historical period, and on the right is the, in the center is the future climate period, and then the difference in the number of days of extreme fire weather is on the right. So, okay, we've done some science. We loaded some of the MACA downscale data. We developed a model. We ran that through our pipeline, and out comes some scientific data. It's great. We have this map. We can take a look at some other ways of looking at this data. So here's looking at the temporal trends. So instead of now making a map, I've taken a look at the time series of these, and we can see that sure enough, the number of extreme fire days goes up on average per year. The last thing I want to do in this notebook is actually take take this data and summarize it and put it into another repository in my catalog so that others can use it. And so here I'm going to create a new data set that is so this is a new xarray data set called summary DS, and it's the extreme days percentage change. So for every pixel, what was the magnitude of the change? So I just created that data set, and you can see it here. There's just one data variable, and it's just latitude by longitude. So it's just a map. And we can visualize that here in Python. We can see that the percent change is largest in the kind of mountainous areas or in the more temperate areas where there wasn't a lot of fire before. But we don't need to do a ton of analysis right now. Just we've created the map. And what I've what I'm running right now is I'm saving that data to a new repository in Array Lake. So here we have a repository called Maca Fire Risk Analysis. I check that out using the Array Lake client. I create a writable session to this branch main, and then I write that data using Xarray's Zarr backend. So that is now written, and what we can do now is go to back to the Array Lake web app and take a look at that data set that we've just created. So that data set was called Maca Fire Risk. And here we can see that smaller data set. It's just latitude by longitude. It's this two dimensions of just over the Western US. You can see this is all the metadata we just added. So that data is immediately in the catalog. I didn't have to do anything special to put it in the catalog. It just showed up immediately. And from here, I can go back to root, and we can actually visualize this data directly in using our map tile server. So map tiles is a way of generating data visualizations on the fly using Earthmover. And here we'll do -100 to 200%. And I'll change the color map. I've been liking turbo. And so we'll say preview. And if I got that right, and I'll zoom in, we can see that this is the same map I was showing on in our notebook, now available to anyone that is maybe in a GIS application or in a web application that can make queries to this same backend. And so, we provide the code for showing you how to embed this in your own application. But the basic idea is this is an endpoint that can be queried from any web application or GIS application. Okay, so that's that. That wraps up the notebook part. I'm going to jump back into the slides here, and we can we'll wrap up. So here is a few summary and key takeaway points for what we've done so far. So the problem is that we identified is that working with these many terabyte size data sets really slows down our ability to kind of do innovative science and data analytics. And so what we did is we ingested before I didn't mention this, but before we did this webinar, I ingested the data from his original big stack of netcdf files. And so we put that data into our catalog using using Array Lake and Ice Chunk, and it makes this kind of massive geospatial data instantly accessible and highly performant. I can stream terabytes of data in just a few seconds. And so that's what we did in the notebook is we, showcase how to use Earthmover with some simple fire risk model. And we did that against a slice of this larger archive of data. So I think with that, I will wrap up. We can take questions, saved plenty of time for discussion, and happy to jump back into the demo and try some things too, if there's interest in taking a look at parts I didn't get to touch. And Cheryl, you'll have to tell me if there's questions because I don't think I'll be able to see.
Okay, there aren't yet, but
Okay,
everybody can access the Q&A on the bottom. And then I think...
Oh, I can't see the Q&A. So yeah.
You can? Okay.
Yeah. Cool.
Yeah.
Yeah, so folks, leave questions in the Q&A. If they're, yeah, okay, so someone named Y Twice, which is a great name for your Zoom account. Yes, we'll follow up with a link to the notebook in an email later today, along with the recording. So. Okay, so the next question from Mariah is, how does IceChunk handle S3 archiving and intelligent tiering? Yeah, so you can tell IceChunk how you want objects to be tagged for different tiers of intelligent tiering. And we have customers doing this today where they say, they specify that. And you can do that in a one-off mode, or you can persist that setting in IceChunk so that all writes to a specific repository will use intelligent tiering. Okay. The next question here is from Arjun, and does the platform allow you to schedule tasks? Yes, but only a certain number of tasks right now, and it's mostly in the kind of automated maintenance of your repository. So what we don't have is just like an automated task scheduler for like code that you write, but we do have a set of jobs that we run on your data that's in the platform. So specifically the tasks around garbage collection of uncommitted data, and expiration of old versions of your IceChunk repository to help kind of maintain the version history and to avoid there being garbage inside the repository that's not accessible. So over time, we're going to build out more functionality like that. And so if like there are certain tasks that you have that are like, do you think would be super high value, shoot us a note. We'd love to hear what those are. Okay, the questions are flying through now. I love it. So Dumai asked, I got tested earlier. So Dumai tested the earlier version of Array Lake, and I'm trying to catch up on, and she's trying to catch up on the work we're doing now. What's the distinction between Array Lake and IceChunk now that this has evolved? This is a great question. So the very first version of our platform used a different backend architecture for doing the data versioning and ACID transactions. And with the release of IceChunk last year, we've moved all of that, that transactional backend of the data format into the purview of the client in the back in the object store. And so what Array Lake remains is the catalog in the access control layer, and IceChunk handles the ACID transactions in the data versioning directly in conjunction with, say, your S3 API. And so that's the main difference of what has evolved in the last in the last year. Cool. Oh yes, and then IceChunk's yeah. So Ryan also pointed out IceChunk's 100% open source, and so that is that's a difference between it being tied directly to the catalog part of the product. So cool. Okay, so Stuart asked, the web map tiles that you were hosting, are those stored on our cloud provider, S3, for example? Okay, so it's a great question. We're not hosting any tiles. We're generating them on the fly. And so, what we've built with Flux is a performant way of generating tiles on the fly for these kind of multidimensional array data sets. And so when I loaded up that web map tile to show you what the output of that one data set was, that was generated immediately on the query. And what's great about that is if I updated the data set, the next query to that web map tile endpoint would show the new data. And of course, you can also specify specific snapshots and that sort of thing. But you don't have to go invalidate your cache of tiles or anything like that. Okay, so then how easy is it to resolve different met grids? So I don't fully understand what you mean here, but Zarr can handle any gridded data. So it is a kind of a generic container for multidimensional arrays. And on the tile side, we handle a bunch of different grid types. And so it doesn't have to just be a latitude by longitude grid. We can do reduced Gaussian grids. We can do triangular mesh, a bunch of other things. So yeah, Ryan got it into the chat as well. So all right, I'm going to move on to the next one. Mariah said, in a forecasting system, would it make sense for the data repo to be set up such that each branch was a forecast init time? I don't think so, but maybe. There might be applications for using branching in that way. We see people using two different models for how to do forecasting. The first is to have a dimension that is the forecast init time, and that you append each forecast along that dimension, or to use separate groups within the same repository. And so you can, in those cases, we see someone have a group for, the 0 Zulu and the 12 Zulu for each day, and so on. So there's different ways of modeling this, and it really comes down to like how you want to evolve that repository over time. Mariah, I'd love to hear more about your forecasting application. And so I'll probably reach out and try to figure out a little bit about what you're solving for there. Okay, so the next question here is there any cost for individuals or education institutions for using the platform? Yeah, it's a great question. Yes, and it depends on what the use is. And so, yeah, there are, we have educational institutions using the platform today. There is also the option of using the product at the free tier, which is in essentially read-only mode. And so there's public data available on the product or on the platform today. Anyone can log in and use it. Where we have decided to charge for is if you want to generate your and organize your own catalog and manage your own data. And so if that is the sort of use case you have, then yeah, there's a cost for it. And if just accessing the data sets that are available on the platform is sufficient for you, then no, there's not. So hopefully that answers your question, Duncan. Okay, so any other questions